Hello, this video is recorded for the course project in Advanced Topics in Deep Learning, realized by Zihao and myself. Let's have a quick introduction of this project. The dataset we use named Wine Quality Red. It has 11 different features of the red wine. Depending on that, we have a score for each of them. It's downloaded from OpenML. And we are going to use some deep learning technique to train this dataset and make predictions. Moreover, we also plan to minimize the loss during the training process by applying neural tangent kernels and its generalization. Mathematically, this equation here, L theta, represents the training loss, which is the term we want to minimize, is the sum of the difference between the prediction and the truth. Pay attention to the theta here, is the total number of parameters. And the gradient of this loss can be easily computed as the second equation here. We will use it later, of course. And through the gradient descent and the chain rule, we get this derivation about theta t. Mu here is the learning rate of the gradient descent, and the gradient term here is just the same as the previous slide. What's more, we will apply Jacobian matrix noted d theta ftx to expand the gradient term as here. And finally, one more time with the chain rule, we got this another derivation of ftx, and here we introduce kt xx here is the neural tangent kernel we want to use, and it's simply the Jacobian matrix times its transpose. A little summary here. Through the NTK theory, neural tangent kernel stays constant during the training process, which means it's stable along time changes, and it's irrelevant to the initialization. We can simply choose K0, the NTK at the time 0, to represent the KT. Then imagine we will use a one hidden layer network to train the RIDE1 dataset, where M here is the width of the layer. In other words, we have M hidden neurons. During the optimization step, we have somehow this kind of equation with only M in the denominator. By the law of the large number, we have considered it as a standard Gaussian distribution, and the value is quite close to its expectation, which means K0 converges to K star, which is a deterministic kernel. And if we use a wide neural network, the training loss of this network converges to 0. And this network should be trained with small learning rate. It should be tested in the practical parts presented by my teammate Zihao after.
Next, I will introduce our practical part view. And first of all, our dataset is the RIDE1 dataset on open machine learning. And this is the first 5 rows of the data. and you can see it has 11 dimension and 1,600 data. And the goal is to classify this grade 1 into 6 grids. And then its property have such as fixed acid decay, critical acid, and pH or alcohol degree, something like that. And then there are some introduction of its data contribution. And you can see that there are the object class is mainly it is mainly 3 level. It's 5, 6, and 7, and and then there are some. Here is the mean variance and other attribute of this of these attributes. And the next step to change this target to integer. And then it's just some adjustment of its data format. And then we use the PCA, but it doesn't make much sense. It's mainly just to regularize the data on each attribute. And next, we just divided the data into training set and data and test set. And then we use the different classification methods such as logistic regression, SVC, and random forest. And it can be seen that the accuracy rate is about 55 to 65%, which is mainly for the purpose to just for the comparison with the deep learning method later, and followed by our deep learning model. And you can see that it's very simple. There is only one full connected layer, and the sigmoid activation layer, and the input is 8 dimensions after PCA, and the output is just 6 dimensions to correspond to the 1 hot of the one hot format of the 6 levels. And the next is the training part, and here we just save the model before training. And then here is the training part. We use the BCE loss functions to compare the one hot vector and the probability of each class using the SGD and using the SGD optimizer. And you can see that our network has an accuracy about 60% on the training set and 65% on the test set. And here is the confusion matrix, which is similar to the previous classification result. And next, we loaded the original method and intending to compare the mirror tangent kernel matrix between the model before training and after training. And in order to compute the NTK, we need a function that takes a model's parameter and a single input and returns a single output. It can be done using functouch making functional. And next, we see that the NTK before and after training have a large difference. We think this is the result of the insufficient width of the neural network. It's just 100. It can be 1,000 and then there will be a smaller difference. And then we calculate the K matrix on the test set and calculate the new linear regression model for the inferred features. And we can see we can use the one-hot target is regarded as we can just regard the one-hot target or as a ordinary vector to calculate the MSE loss. And then finally the one-hot is resolved to obtain the classification result. And next, here is the result of the original model after training, and here is the result with the linear regression model of NTK matrix. And we can see that the correct rate of the model calculated using the NTK method is 98%, which has been greatly improved. And here is also the conclusion matrix.